Okay, so next we're going to take a look at reactions of aldehydes and ketones. And the first reaction that we're going to look at for aldehydes and ketones is going to be hydrogenation. And we saw hydrogenation of alkenes earlier on in this class. And the general reaction for the hydrogenation of an aldehyde is that the carbonyl carbon, sorry, the carbonyl functional group is going to be reduced to an alcohol. And so if we take an aldehyde, we end up reducing to a primary alcohol. Now you remember that reduction is the addition of hydrogen, right? So you can see this is a reduction because we're adding hydrogen, but we call it a hydrogenation reaction. And you can see that these two hydrogens, one ends up on the carbon, that was the carbonyl carbon, and the other one ends up on the oxygen, that was the carbonyl oxygen. So again, aldehyde gives you a primary alcohol. And you see an example here with propanol being reduced to 1-propanol. We see that the carbonyl carbon, if I highlight it in blue, okay, it has one hydrogen attached to it, but after the hydrogenation, it has two hydrogens attached to it, and the oxygen from the carbonyl takes on hydrogen. So hydrogenation of an aldehyde again gives you a primary alcohol. We have a ketone on the other hand. So the ketone that we're using here is acetone in the example, but if we have a ketone, we're going to add our two hydrogens to our carbonyl carbon. We add one to the carbon and one to the oxygen, and we get a secondary alcohol. So again, I'll repeat, a ketone will give us a secondary alcohol, and the example that they show here is acetone undergoing hydrogenation to produce 2-propanol. And so in example 10.2, it says benzaldehyde, the main flavor component in almonds, can react with hydrogen. Show the formula for the product of the following reaction. So we have our benzaldehyde, we're reacting it with hydrogen. And so what's going to happen is our aromatic ring is going to remain intact. But now the carbon, that was the carbonyl carbon, is going to have not one hydrogen attached to it, but two. And the oxygen from the carbonyl will have an a hydrogen attached to it. So we went from our aldehyde, benzaldehyde, to a primary alcohol, right? And we can see that this is a primary alcohol because the carbon that has the oxygen attached to it is attached to only one carbon in our structure here. Now, the way I drew this primary alcohol, there's nothing wrong with it, but um, a quicker way to draw this bond line structure would be just to do something like this, okay? This compound, it has a name, it's called benzyl alcohol, which is neither here nor there. What you have to remember is that an aldehyde is going to get converted to a primary alcohol. All right, so moving on to oxidation, the difference in reactivity toward oxidation is the chief reason aldehydes and ketones are classified as separate functional groups. Aldehydes are readily oxidized to the corresponding carboxylic acid, while ketones resist further oxidation. And so you see here that if we take a primary alcohol, and we saw this earlier on in the class, if we take a primary alcohol and we oxidize it, remember this O in brackets here, this just represents oxidation. Remember, the oxidation is the loss of hydrogens or the gain of oxygens, and you can see that we're losing two hydrogens as we go from this primary alcohol to the aldehyde. However, aldehydes can be further oxidized to a carboxylic acid. And again, we saw this earlier on in the class when we talked about alcohols, and you see a specific example here of benzaldehyde, and it's undergoing oxidation to give us benzoic acid. So you see that it's gaining an oxygen in the process. And remember, I said the oxidation was either loss of hydrogens or gain of oxygens. Okay, either one counts as oxidation. Now, when we oxidize a secondary alcohol, and again, this is something that we looked at earlier on in the class, okay, when we oxidize that secondary alcohol, we get a ketone. However, ketones, unlike aldehydes, do not undergo any further oxidation, okay? So if you take something like acetone and you try to oxidize it, you're going to get no reaction. Nothing's going to happen. So I repeat, an aldehyde can be oxidized. but a ketone cannot be oxidized. Okay, so aldehydes get oxidized to a carboxylic acid, but ketones will not undergo oxidation. Okay, example 10.3. Cinnamaldehyde is the compound that gives cinnamon its characteristic aroma and taste. Draw the structural formula for the oxidation product of cinnamaldehyde. Well, they've given us the structure here. You can see we have a few functional groups. We have an aromatic ring here, aromatic. We have an alkene here. There's an alkene. I'll just scribble it up here. But then you see that we have an aldehyde. Okay, we have an aldehyde and it's undergoing oxidation. And so we know that aldehyde is going to get oxidized to a carboxylic acid. So we're going to redraw our aromatic ring. We're going to put in our alkene, but that aldehyde, we're now going to insert an oxygen in between the carbonyl carbon and the hydrogen. Okay, so now you can see that this is what I'm circling here in yellow is a carboxylic acid. Okay, next is reduction, and reduction is the opposite of oxidation, meaning what we're going to do is we're going to take a carbonyl compound, meaning when we talk about carbonyl compounds, we mean aldehydes or ketones, and they're going to be converted back into their corresponding alcohol. And so reduction increases the number of bonds between carbon and hydrogen. And the most effective reducing agents are sodium borohydride, and you can see the formula for sodium borohydride is here, NaBH4, and also lithium aluminum hydride, and you see the formula for lithium aluminum hydride here. What we're going to see in these reactions here is to represent these reducing agents, all we do is we just put R in parentheses like this. So the general reaction for an aldehyde is shown right here. We take our aldehyde, so there's our aldehyde, and then we treat it with our reducing agent. And so our aldehyde, so again, this is our aldehyde, gets converted into a primary alcohol, when it undergoes reduction. And so you can see here benzaldehyde being reduced to benzyl alcohol, and you notice that we're adding 2 hydrogens along the way. And I didn't say it for the first example, but you see we're adding 2 hydrogens here. Anyhow, then if we have a ketone, when a ketone undergoes reduction, it gets converted into a secondary alcohol. So we have our ketone, and we end up with a secondary alcohol. All right. And you can see again that we added what? 2 hydrogens along the way. And the example that they're showing here is acetone being converted into 2-propanol, which is also known as isopropanol, a rubbing alcohol. And we saw that earlier on in this class by the addition of the 2 hydrogens like this. So remember, when a reduction occurs, all you have to do is look at the carbonyl group, okay? And the carbon of the carbonyl group is going to take on a hydrogen, okay? And then you're also going to add a hydrogen to the oxygen of the carbonyl, and you're going to remove the double bond. So that's essentially what's happening here, right? Originally, there was a double bond here, but then we remove that double bond and we attach a hydrogen to the oxygen. So that's our reduction. Okay, question 10.4 says, draw the structural formula for the reduction of the product of cyclohexanone. And cyclohexanone is often used as an adhesive in PVC, polyvinyl chloride. Um, there we go. So what we're going to do is we're going to do our reduction. So if we look at the carbonyl, okay, on the carbon of the carbonyl, we're going to add a hydrogen. And then on the oxygen, we're going to add a hydrogen. And we're going to remove that double bond. And so what our product will look like is it is going to look like this. So now we're going to have no double bond. We've got a hydrogen on the oxygen, and we also add a hydrogen here. And you can leave that hydrogen in if you want, but it's not really a proper, technically proper bond line structure. So you could also write it as this, just draw cyclohexanol like this. So you see we go from cyclohexanone to cyclohexanol. And again, you see here that your ketone is being reduced to a secondary alcohol. And so students will sometimes ask me, oh, do you have a summary of everything that we've covered? Well, here's a reaction map or a summary of the reactions that we've looked at for aldehydes and ketones. And we've looked at three different types of reactions. We looked at hydrogenation, we looked at oxidation, and we looked at reduction. So we started out with hydrogenation. And if you have an aldehyde that undergoes hydrogenation, you end up with a primary alcohol. However, if a ketone undergoes hydrogenation, you get a secondary alcohol. All right. Then if we just skip the oxidation and go straight to the reduction, you see it's very similar to the hydrogenation. And then if you reduce an aldehyde, you get a primary alcohol. And if you reduce a ketone, you get a secondary alcohol. Then if we look at oxidation, well, ketones do not undergo oxidation, so we don't have to worry about anything there. But an aldehyde, we saw that an aldehyde can be oxidized. Oops, an aldehyde can be oxidized. So I'll put here O to what? To a carboxylic acid, right? So to a carboxylic acid. So that's a summary of all the different reactions we've seen in this video.